Okay, so hey guys, welcome to Clean Coder YouTube channel. Today we're gonna solve LeetCode problem number 45, Jump Game 2. As usual, I'll be walking you through the problem description, and then we're gonna solve this problem via brute force solution, and then I'm gonna show you the slightly tricky the optimized solution for this problem, which is very difficult to come up in a interview, but let's try our best to know the optimized solution. So I'm only gonna walk you through the solution, and I'm not gonna code that solution. Only gonna show you the solution which I was able to come up in like 20-25 minutes. Okay, so let's start. So the name of the problem is 45 Jump Game 2. The problem statement is an extension of Jump Game 1. So if you haven't seen the solution for Jump Game 1, you can watch that video first, and then you can try solving Jump Game 2, as Jump Game 2 is slightly, I would say, advanced than the Jump Game 1. Okay, so without wasting much time, let's read the problem statement. It says you are given a zero indexed array of integer nums. The length of the integer is n, and we are currently at the first index of the array, and each element pretty much represents the length of forward jump from index I, or in other words, if you are at nums of I, you can jump to say nums of I plus j, where j is anywhere between 0 to nums of I, and I plus j is less than n. And what our goal is to return minimum number of jumps to reach the last index of the array. Okay, we have to return the minimum number of jumps with which we can reach the last index of the array. Okay, so I'm gonna walk you through with the test case. Let's try dry running something, or let's try visualizing this problem with the test case 23114. This is our test case 23114. Okay, so what's the minimum number of jumps with which we can reach from here to here? Okay, so let's say I'm standing here at 2. So where I can go here at the first index, or I can go at the second index, right? With the 2, right? I can either go here or I can go here. Okay, so let's say I go to the first index. Okay, I go here. Okay, now from here I can pretty much reach the destination directly, right? Like a jump in this fashion. So in 2 jumps I can reach the destination, right? So 2 is the answer for this test case. Let's see another test case 23014. Okay, so again from here I can go to these 2 positions directly, right? Let's say I choose the first position, so I'm here, so I have consumed 1 jump, and then from here I can directly reach the destination, right? Like this. So again, in 2 jumps I can reach the destination, and 2 is pretty much the answer for this problem. So let's think about the brute force solution for a moment, how we can solve this problem in a brute force fashion. So the solution which I was able to come up with is mix of I would say dynamic programming and brute force, but it's also fine, like in interview setting. Even if you are able to get a solution like this, I think it's good enough for getting started. And if the interviewer really want you to optimize up till the optimal solution, I think he is gonna give you some hints, but even this solution is good enough if I would be the interviewer. So what we are gonna do is, let's say we have a test case like 2, 3, 0 1 4, right? 2 3 0 1 4, correct. What we are going to do is we're going to make a auxiliary array of same length like this. Okay, we're going to make an auxiliary array of this length, right? What we are going to do is mark the first position as 0 and mark all other positions as infinity. We are going to minimize the other position as we iterate through our initial array, right? 0 is where we are standing currently. Okay, so I'm here right now, right? So from 2, where you can go? You can either go here or you can go here. So instead of infinity, mark this as 1, mark this as 1. Okay, so now let's come to the second index. So from here, where we all can go, right? I can go here, I can go here, I can go here. Okay, so here you can pretty much reach here, like you can reach this spot in one jump, right? That is good, that is the minimum. Now here you can reach in how many jumps? This plus 1, right? This plus 1, so which is 2, right? And here you can reach this plus 1, which is 2. So here you can reach in 2 jumps. That is the answer, right? That is the optimal. So this is a combination of, I would say, brute force plus dynamic programming, because we are using some already computed information to decide a further state, right? So this is a combination of dynamic programming and our brute force approach. So without wasting much time, let's try coding this solution, and then I'm gonna walk you through the optimal solution also, and we are not gonna code that. Okay, so this is my browser, right? Let me expand the window for coding a bit. This is my window. So first of all, let's handle that case, the corner condition, when the length of the array is 1. So we know that pretty much you don't need any jump if the array is of single length, right? So now let's move forward. Let's declare our auxiliary array first. Aux new int nums dot length for int I equals to 1, I is less than aux dot length I plus plus. Okay, aux of I is equals to integer dot max value, as I told you, the initial state, right? For int I equals to 0, I is less than nums dot length I plus plus. Start is pretty much the I plus 1, the next index, right? And similarly the end is tricky. End is you have to take mat dot minimum here. I'm gonna tell you that in a moment. You have to take mat dot minimum here because it can easily cross the array index. Like I had one array index out of bound exception because of this corner condition. So you have to take this, you have to keep this in mind somehow, that end needs to be inside the bounds of the array. So now this is the straightforward loop, right? J is equals to start, J is less than equals to end, J plus plus. Okay, aux of J is equals to math dot minimum, aux of J comma aux of I plus 1. It's same logic as I have described you in my whiteboard, right? Now let's come out of this loop and let's return the last element of the auxiliary array, which is pretty much the answer. Length -1. Okay, so this is the code. Before submitting, let me tell you the time complexity of the solution. The time complexity of the solution is order of n squared, right? I'm using a kind of nested loop, so it's order of n squared, and we are using auxiliary space also, so space complexity is order of n, right? So these are the trade-offs of time and space. Let's try submitting this problem now. So I'm gonna run it first. Good, it got accepted. Now let's submit. Nice, very good. So it's like the problem statement is solved at this point of time, but the thing which you can see is that the runtime is very bad. It's 27 millisecond and it beats only 20% of the LeetCode population, right? So clearly our solution is not optimal. And why it's not optimal, now I'm going to tell you the reason why it's not optimal. If you think carefully, right, in this problem, why I called brute force here, right? It's because we are pretty much checking everything from start to end, right? We are checking unnecessary. We are doing some unnecessary computation. Instead of brute force here, we can do BFS. So this is essentially a problem of breadth first search. So if you can construct a graph, right, of all the nodes, and if you do a BFS in that, right, pretty much we know that BFS gives the shortest path, right? And this is actually a undirected graph, and what the problem statement is asking us is to compute the shortest path in that undirected graph, right? Just that the graph is in the form of array, and we somehow have to become creative that without doing without making a graph, like without wasting time to make a graph, we have to compute directly the BFS, right? That's the caveat in this problem. So this was the crux of the optimal solution. Now let me tell you the optimal solution also. I'm going to write it on the whiteboard. You can like verify that. Like I can give you a gist of that solution. Maybe I'll try to dry run it on a test case, but I'm not going to code it because honestly I was not able to come up with this solution in 20-25 minutes. So yeah, let's go through the let's go through the solution together. And I'm also learning this technique. This is awesome technique. So what the guy did was, like the guy who solved this problem in optimal way is that he did the BFS implicitly. So let me show you the code, and then you're going to understand how he was able to compute this implicitly. So public int jump, this is the signature, right? Int, this is the array. What that guy did was he took 3 variables, jumps, and then he took the variable current end and current farthest. Okay, current far, let's take this, right, 0. Now what this guy did was he did a for loop. I is 0, I is less than a dot length -1 I plus plus, and what he did was here, if I is double equal to current end. So I'm going to explain you what he is actually doing in a moment, but right now just focus on the code, how the code is getting generated, code is getting populated. Okay, so current end is equals to current farthest now, and in the end what he is returning, he's just returning the jumps. Okay, so if you think like it's like this thing he is doing, right? So instead of doing brute force for all the elements, he has kind of pruned the space, search space, right? He's only computing the states which are relevant, right? Which happens in BFS. And what he's doing with the current end and current far, these are just like in BFS, if you implement it via queue, you like in order to keep the count of from where the queue is starting and where the queue is ending, you need the end markers, right? Which are the number of elements in the queue. So he's using current end and current far as those markers, and whenever the queue gets exhausted, right? Whenever the queue gets finished, I is at the current end. That is the condition when queue gets exhausted. So he makes jumps plus plus and he moves to the next level and he computes current end as current farthest. That's what he is doing. Okay, and one line which we missed here is current farthest. Okay, current farthest is equals to mat dot maximum current value of current farthest comma I plus A of I. Like both the markers will increase, right? Current end will also increase, current farthest will also increase. Current farthest he is increasing every time he is iterating in the array, and current end is only incrementing whenever the level gets completely exhausted. That's the magic of his code. It's nothing but kind of level order traversal in the tree, slightly creative and I would say slightly clever approach. So the time complexity of this approach comes out to be order of n and space complexity is order of 1. So this is the cleverness in the optimal solution. So if you like this explanation and if you like this kind of walkthrough, do give this video a thumbs up, and I'll see you the next time. Till then, bye bye.